Hello, everyone. I'm Devon. I'm from the Electric and Computer Engineering Department at North Carolina State University, and this is towards continuous plant bioimpedance fitting and parameter estimation. So we are looking into precision agriculture and smart farming. So the idea here being we can have a device on individual plants. It sends us information that we can fit curves to. We do some data processing and predicting based on that and give the plant the necessary water or nutrient requirements. Specifically, what we did is model fitting with equivalent circuits. We developed a rudimentary data pipeline, and we end by testing a couple of different potential weighing schemes and objective functions. To provide some intuition, we developed a small GUI here. So you can see in red is the data points from an impedance curve, and then in blue is the model that we're using to fit. So we can get a pretty good estimate just by eye of how the model should behave, but we're really looking into automating this process. We used plants in typical conditions. They were raised slightly above room temperature. On the impedance side, we sweep logarithmically 10 per decade from 5 hertz up to 500 kilohertz. And this was measured every 10 minutes over the course of a few days. So that's how we end up with the longitudinal data. We use two models, the single shell model on the left. This one permits current to go either around cells or through cells. If they go through cells, they have to pass through the membrane, which acts as a capacitor. So we end up with an RRC circuit. The double shell model builds on this by adding another path where the current can go through the vacuole. So we actually model the vacuole, which can be quite large in some plants. So we end up with 3 pathways and an extra RC attached to this single shell model. The official problem statement is made here. So we are looking to minimize L, which is the sum of the square errors. Impedance is a complex value, so we have a real and imaginary components that we have to do this across. And A and B are the weighing parameters that we can use, so we can weigh evenly across frequency or dimension being the real or imaginary part. We make a couple of comparisons between the single shell and double shell, real and imaginary versus the equivalent in terms of magnitude and phase, and a couple of different weighing schemes, weighing evenly across frequency or dimension or the boundary conditions. But what I want to point out here is that the double shell model at high frequencies fits the data a lot better. And this suggests that the vacuole is indeed necessary in the model. We compare all the models against each other using standard metrics. The thing I want to point out is that the double shell model performs better in every single metric than the single shell model. So we'll probably be going with that one. Putting this all together, we can end up with a time series of individual parameters. Shown here, we have parameter R2. Over time, we can see it didn't change much, but we do get longitudinal data from that. And this work was supported by the USDA and a couple of different groups here at North Carolina State. And thanks for stopping by.